so today we'll revisit this mean field theory for the Ising model. Right. So just to recapitulate some very simple points. So all of you remember how we got till the mean field theory of the Ising model, right? And basically, then we got sort of a free energy for this mean field theory. And this free energy had the interesting property that it gave a critical temperature above which it looked like this. If you plot it as a function of m, and this m needs to be determined self-consistently, okay, as we saw, right? And below which it actually looks like this. Below TC, it looks like this, right? So below TC, basically, there was one unstable point and two stable points, if you wish, for this free energy. And basically, these two are the two spontaneously symmetry broken phases of the Ising model. Okay, and above TC, of course, you only get one phase, which is the disordered phase. Okay, so D equal to 1 in the one-dimensional Ising model, we saw that there's no phase transition. Whereas for D equal to 2, we actually calculated the TC using a duality. Okay, you remember we used a high temperature, low temperature duality to calculate the TC, and that was not non-zero, right? And we said that the mean field theory result is basically an exact result if you consider the infinite dimensionalizing model, okay, on a hypercubic lattice. Okay, so of course we can easily imagine like a 2D lattice or a 3D lattice like this. But then, of course, we can mathematically extend it to a d-dimensional lattice as well, d-dimensional hypercubic lattice as well, right? And as this d becomes larger and larger, the mean field theory becomes more and more exact. In fact, we also made the statement that if I look at the critical exponents near the transition for any d greater than equal to 4, greater than or equal to 4, then we'll actually get the mean field theory exponents. Okay, we'll get that. But of course, if these 3 or 2, we'll get different exponents. That's what we saw, right? For 2 dimension, of course, we have Onsager's exact solution. For 3 dimensions, we have basically other methods, primarily Monte Carlo methods to calculate the exponents, right, to a great accuracy. And from both, we see that they are non-mean field exponents. Okay, so that's where we stopped last time. So today, and whatever time we have this week, we'll learn two important things, a few important things rather. First, let me show you today why this is true. Why is mean field theory exact when the D is much larger than 1, when the dimensionality of the system is much larger. Okay, I mean, this, of course, we intuitively argued, right? Remember that we said that, okay, you have a spin, and basically the mean field is generated due to all the neighbors of that spin. And of course, in the limit when the dimensionality of the system is very high, there is a very large number of neighbors. And then what you can do is ignore the fluctuations of this field that is produced by all these spins on this spin, right? Because the mean field theory assumption was that you basically ignore certain fluctuations at second order. If you remember, you ignored these kinds of fluctuations in mean field theory. You ignored these, and that's how the theory became. So of course, there's an approximation, but with this approximation, the theory became solvable. Okay, so I hope you remember this. If there is any confusion till this point, just ask me. And of course, I also showed you how to calculate the exponents within mean field theory, the critical exponents. So if there's any confusion till this point, just ask your question or confusion. So, okay. So yeah, if there is no confusion, that's good. Yeah. Okay, so actually, just like you, I'm also a stranger to online classes, right? So it'll be good if someone says something, right? It may be also like a no, there's no confusion, but yeah, okay. Anyway. Okay, let me go on. So let's try to understand this limit. Okay, so here we already see one interesting point. So suppose my Hamiltonian just has the magnetic term, right? This guy. So I'm writing capital H for a reason here. So this is the normalizing model. This, of course, we know how to solve, right? But suppose I now write our favorite term here, which makes the theory interacting. Suppose I write a term like this. Okay. And I also tell you that I'm writing this term. So, of course, you remember the meaning of this symbol. This symbol just means nearest neighbors, right? This symbol. So now, suppose the dimensionality of your system is very large. Okay, let's say it's a 10,000 dimensional hypercube. Then we know that in thermodynamics, the left hand side, the Hamiltonian or the energy needs to be extensive. Okay, but on the right hand side, there's a bit of a problem. Okay, so the problem is that in this limit, each point is basically, if you wish, interacting with many other neighbors, right? A huge number of neighbors, right? So each of these things is scaling as whatever. So each I is connected to an order D number of points, right? And then there are order D number of points itself on the lattice, right? So actually this part of the energy is scaling as order D square. Why is it normally not the problem? It's normally not a problem because unless you take this kind of a limit, this number is always finite, right? So let's say you're in 2 dimension, then this number is 4. If you're in 3 dimension, this number is 6, right? So 4 times order D is still an extensive number. 6 times order D is still an extensive number, right? But suppose you want to push this number to infinity, then there is a problem because then you're actually multiplying order D with order D. So that's order D square. So that's not extensive. That's not extensive. Therefore, to tackle this limit, I need to do something to this term. Okay, I need to do something to this term. So what do I do? So basically, in the large D-dimensional limit, I'm basically saying that each point is interacting with the other points in the lattice. That's what really is the meaning of D tending to infinity. Okay. So then, to normalize this term correctly, so that everything stays extensive, I need to do this. So n is the number of spins on your lattice as usual, right? And then basically I can just put something like this, and then everything interacts with everything else. Right? This is basically what happens when D tends to. Is this point clear? Why am I normalizing things like this? So that I'm normalizing things like this so that even in this limit, like energy is extensive, which is a necessary condition for thermodynamic phases. Is this clear? So usually we don't do it because the number of neighbors is finite, right? Suppose you're in 2 dimension or 3 dimension or 4 dimension. But if you're in a very high dimension, then you need to do this. Otherwise, the energy is not extensive. Is this clear? Yes, no? I mean, somebody should say something.
Not clear, sir.
Sorry, what?
Not clear, sir.
Not clear. What is not clear?
Sir, why in this case order D and...
No, because the number of neighbors is also scaling as order D, right?
Why it is then why it is extensive in its finite dimension?
No, it is extensive. It is extensive because see, in finite dimension, suppose you're in 2 dimension, right? Suppose you're in 2 dimension or in 3 dimension, then this is not order T anymore. This is a number like 4 or 6. How many neighbors do you have in a two-dimensional lattice? Nearest neighbors, 4. Right? In a three-dimensional lattice, you have 6. But now the problem is, when you're increasing this like this, the number of neighbors that you have, right, is increasing in the same manner as the number of lattice points. You see, that is the problem. Okay, both of them are scaling with order D. Therefore, the entire sum is scaling with order D square. So therefore, you need this normalization here. Is that clear?
Okay.
Okay. Okay. So basically, to imagine this limit, what you need to understand, what you should think about is that they are basically endpoints. They're basically endpoints. And each point, so let me use a different color. Each point is interacting with all the other points, like this. You see what I'm doing, right? Each point is interacting with all the other points. Because in this limit, basically you lose your sense of locality. All the distances are equally likely. Okay, so that's the point. So each point is basically interacting with each other point. Okay, so but here also, if you take this normalization, then everything is okay. Okay, the energy is extensive. So of course, this is an artificial problem. But what I'm going to show you is in this artificial problem, so this is of course artificial, right? This is artificial. But in this artificial problem, I'm going to show you that mean field theory is exact. That's my motivation. Okay. Then when you take D tending to finite, any finite D, then there are always corrections on that. Okay. And then mean field theory is not exact. Okay. Is this point clear? Why I'm choosing this Hamiltonian? Anybody else? Is it clear? So Orkomitra said it's clear to him, but somebody else should also comment.
Sir, YBS means we have seen that for D greater than 4, the mean field theory works.
No. We have not seen that. We have only seen that for D greater than 4, and I did not explain it to you why. We have only seen that for D greater than 4, the exponents of the mean field theory are the same as the actual exponents. We have only commented on that. We never said that mean field theory is exact. We never said that.
Okay, over here, exact means, sir?
Exact is only one meaning in life or in English. I mean, you open a dictionary, it has only one meaning. Exact means exact. I mean, how do I say it? Exact means that the partition function is the same in the context of statistical mechanics.
Okay.
Right. See, the partition function may not be the same, but still the critical exponents may be the same. Do you understand this point?
Okay, got it, sir. Got it.
Yeah. So just because the critical exponents agree does not mean that the mean field theory exactly describes a particular dimension, right? Okay. Because the critical exponent is only describing sort of the power law with which certain quantities are approaching the critical point. Those power laws may be correct, but the actual numbers may not be correct. Okay? Yeah. Okay, good. So let me do this exercise for you now. So now I have hopefully defined the problem for you. You have capital N points. Okay. And each point is interacting with each other point on this lattice. That is the meaning of infinite dimension. Okay. But to keep the energy extensive, the coupling or the bond strength is just J divided by N. It's not J. It's J divided by N. Of course, I don't need to do anything to the magnetic term, because the magnetic term is a non-interacting term. It's always extensive. I don't need to worry about it. There are capital N spins. Of course, the magnetic term scales like capital N. There's no problem. The problematic thing was here, but I've resolved the problem. Okay. So now let me do some tricks for you and solve this problem. First trick. So let me rewrite this Hamiltonian in a slightly different way. So this notation means every point interacts with every other point. Okay. So apart from some constants, I'm just rewriting this Hamiltonian like this. Is this step clear to everyone? Why am I doing this? Is this clear or not? Please tell me. So I'm rewriting this term like this, and then please notice the 2 here. Yeah. Of course, these SIs have the property just like the usualizing model, that they are like numbers like this. So is this clear? Why am I writing this like this? Is it clear?
Yes, sir.
Okay, very good. Is there anybody?
Sir, can you explain it once?
No, yeah, okay. Yeah, this is very simple. So what is this? This is sum over all spins, right? So if you expand this, you'll of course get terms like S1 square plus S2 square plus dot 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 plus S1 S2 plus S2 S1 plus all kinds of other terms. These terms I can ignore. They're just ones. So they're constants, so I can ignore them. What about these terms? So there is an S1, S2, there's an S1, S3, and so on, all kinds of interactions like this, right? But there's also an S2, S1 corresponding to each S1, S2. Therefore, I need a factor of half. So is it clear?
Okay, got it, sir.
Yeah. Okay, good. So then my partition function in this limit is simply this. In this limit. It's just this, right? Okay, now I'll use a simple trick. So the trick is, yeah, I'll somehow try to make this term linear rather than quadratic. So this is quadratic here. So the trick is this. I just use this Gaussian approximation. Oh, sorry, this Gaussian integration. Okay. So you see, so this is a very common trick in field theory. Okay, and unfortunately, I'm blanking out right now, so I cannot remember the name of the trick. But okay, the idea of the trick is the following. So basically, suppose there is something which is quadratic here, and I want to write it in some linear fashion. Okay, then basically the idea is you introduce some other field. Here the field is x. Okay, and that's like some auxiliary field, and you can integrate over that field, and then of course you get a quadratic curve like this. But the advantage of introducing an auxiliary field like this is then this quadratic term appears as a linear term here. So people often get mystified when they see this thing for the first time in field theory, but it's just this. Okay, it's just this trick. Okay, very simple trick. This Gaussian integration equals this, and I have introduced a dummy variable x here, and yeah, so you'll see why this is helpful here. So I want to apply this trick to this guy, right? This guy, this exponential of this thing, right? This guy. So if I apply this trick, then all that I would get is, so basically I'll just rewrite this term like this. Taking care of the normalizations, I would get something like this. Plus beta j in si. Okay, this is the full thing. Okay. So this guy is, sorry, let me write it clearly. This guy is, okay, this guy. So I'm not using anything more than this standard result of Gaussian integration. Okay, so this is the extra field that I have introduced in the problem. Okay, this is the extra field. And
So
just,
what
yeah.
is the field here? I mean, this.
What is the field? It's just a mathematical trick. That's it. It's just this.
So it's a continuous.
Of
variable.
course. This is a continuous variable, right? Yeah.
Okay.
Correct. This x is a continuous variable. Because unless it's a continuous variable, you cannot do a integral here, right? So yeah, so this m is a continuous variable. Correct. Okay? This m is a continuous variable. It's not a discrete variable. So m has the range minus infinity to plus infinity. Okay? Yeah. Okay, good. So why did I use this trick? Because then the partition function can be written like this. Okay, and then there is a bracket open. Yeah. So let me try to write it clearly. It's a bracket open. Sorry, S equal to plus minus 1 beta j plus. So if you just do this algebra, you will see that everything follows here. Okay, like this. Like this. Okay. Because this term is easy to solve now, right? This term is very easy to solve. Now I have made it linear. See, when it was quadratic, it was hard to solve, right? But now, what am I doing? I'm inserting an extra field, but then the advantage is I have reduced this term like this to this, but this is nothing but a free spin problem because it's summation over ISI. So then I can solve this, and then this is your contribution due to the linear term, right? That's the advantage of introducing this thing. Okay. So when you do that, is this clear? Why I did this algebraic trick and why I can write this now?
Yes, sir.
Okay.
Sir,
Yeah.
sir, after this, are we again going to put that it will be means that linear term inside it and put an integral?
Sorry, I did not understand. What is the question? I did not understand the question.
Sir, I was saying that we just did this entire trick to make that term linear, which was quadratic.
Correct. And after making it linear, we can actually just resum this term, right? Because it's a non-interacting bunch of spins, right? Yeah, that's why I could write this term, right? This term, raised to the power n. Okay.
Yes, sir. And after now we know this term and we can put it back and integrate over the m to get the.
No, that we'll see. So let me continue with the algebra. So you can just simplify everything now. Now you know how to do this term. This is just some Cauchy hyperbolic term. So you simplify everything. I'll come to your question because that's exactly what I'm going to do. So then the entire integral looks like this. Okay, I just rewrite everything. The entire integral looks like this, where, let me explain the symbols to you. So these guys, this is some reduced temperature. This is some reduced magnetic field. And this A has a very interesting form. It looks like this. Oh, sorry. This. Okay. So I haven't yet solved the integral over m. Okay, but I can just simplify this line to this line, and then I get something like this. Okay. So far, I hope there is no confusion. I'm just doing straightforward algebra. But now, look at the very interesting thing. Look at the structure of A of n. Have you seen this expression before? Where? Free energy where?
So when we talked about that domain wall problems,
No, it was also the free energy kind of structure in mean field theory. If you just
Yes,
go
sir,
back
mean
to your
field theory,
notes,
right?
right?
Ajay, yes,
Yeah.
Right. So you see, but now we are not at the end of the line. Now there is a very crucial step, which Orko Mitra was asking me. See, this integral is still a very difficult integral to solve. But now there will be something which will save us. I want to do this problem in the thermodynamic limit. Okay. So then this capital N is a very large number. And then you can solve this integral using the steepest descent method. Okay, because basically what would contribute is the extremum of this function a of m and the expansion near the extremum. Everything else will be damped out because this n is so large. Is this point clear to you? I hope you have done these kinds of things before. Steepest descent in mathematics. Is it okay?
yes, sir, got it.
Yeah, so you see, this is the crucial step. This n needs to be very large, right? But what is the meaning of n being very large? The meaning of n being very large is you're actually taking this problem, this artificial problem, where d tends to infinity, right? Because when d tends to infinity, the number of neighbors connected to each point also diverges, right? Now, what is the number of neighbors in this problem for each point? Capital N. Now you want to take the limit of d tending to infinity. So you want the number of neighbors to diverge. So you need to take this limit, right? So you see everything else comes together now. Good. So now there is a standard way of doing it. Now you just differentiate this function. And find this m star. Now see, very nicely you'll just get this equation back. But you're all familiar with this equation. This is the mean field theory expression, right? When you solve for this thing. And then you can expand this guy. Like this, plus half double derivative at m star, m minus m star square. Of course, there's no linear term because it's extremum. And then the higher order terms, let me ignore. Okay. So then the partition function by doing this trick of steepest descent just becomes this. Let me write the rest of the integral here. The next line. Plus higher order terms. But this integral is just a Gaussian integral, right? So I can solve it. So when I solve it, basically I'll just get this plus higher order terms, which I've ignored in this calculation. Okay. And now because I know the partition function within this approximation, of course, now taking all these n tending to infinity and all, this is not an approximation anymore because when n is really large, then I can justify dropping this term. Right now, this is a very precise statement. Okay, so then the free energy per site, I normalize it like that, is nothing but this. Plus order 1 by n squared term. But look at this expression. This is just the free energy that we got using mean field theory, because of exactly this. This, if you just go back to your notes, you will see that this was exactly the free energy that you got using mean field theory. Okay, right? So hopefully, I've convinced you that when this limit is approached for a hypercubic Isaac model, mean field theory becomes exact. What does that mean? That means that the partition function becomes exactly this plus higher order corrections, which you can ignore. Is this clear to everyone? So this is the first thing I wanted to show you.
Sir, we can only neglect the higher order terms in the Taylor expansion when n is infinite.
Correct. So see, there are two steps. Let me again highlight those two steps here. See, first step is, in my mind, I was doing the d tending to infinity problem. In the d tending to infinity problem, the concept of a neighbor is lost. Okay, because you see, when your dimensionality is very high, each point is actually interacting with each other point. Okay, so that's why I drew this. That's why I drew this picture, that each point is interacting with each other point where there are capital N points, and then to preserve the normalization of, the extensivity of energy, I put this thing here. Okay, so this was the first simplification I got. Doing this, I could write the Hamiltonian like this. Doing this, I could write the Hamiltonian like this. You see, I cannot write the Hamiltonian like this if my coordination number is finite and some point only interacts with, let's say, 4 other points or 6 other points or 10 other points. Then I cannot do this. Okay. So this was the first simplification that I achieved. Then, after achieving this simplification, I used this simple trick, but this is a very well-known trick. You will soon encounter these things in field theory. I replaced this quadratic term by this linear term, but the price I paid was I introduced an additional field M. Okay, the price I paid was that I introduced this additional field M. So yeah, fine, good. And then I could do these integrals, right? I could do these integrals. Why did I do why am I able to do these integrals? Because then my integral has a structure like this. And then I just push this n to infinity. Okay, to the thermodynamic limit. And then it just becomes the steepest descent integral. Okay, so there are two things I have done to actually solve this problem. One thing is this thing, or if you want pictorially, this thing, that each spin interacts with every other spin. That is exactly what happens when the concept of neighbors is gone, which is what happens when d tends to infinity, right? Then you cannot say that, okay, this is my first neighbor, second neighbor, everything is interacting with everything else. Okay, right. So this is the first thing. And then I can solve this integral because n is large. I want to take the thermodynamic limit, and then this integration is easy to do. If n is small, then this integration is not easy to do. But if n is large, I can do this integration just by expanding a of n. Okay, so these are the two crucial algebra steps that help me derive mean field theory exactly in this limit. Is this clear to everyone? This is what I did. Is this clear? Sorry, can you tell me if it's clear or not?
Sir, what would have happened if we didn't, add the j by n in the first case? Then
the problem would not have an extensive energy, and there is no thermodynamic limit to that problem. As you know, in statistical mechanics, energy needs to be extensive. Yeah, it would not have been extensive. So so that doesn't make sense.
Okay, sir.
Sir, when we take the coupling constant to be j by n, and then we have n becoming very large, so the coupling between spins also becomes weaker as the dimensionality increases, right?
Yes, of course.
So at some point, can it become completely negligible?
No, but you see, that's where you need to take limits very carefully. Of course, it becomes smaller and smaller, but the number of neighbors also becomes larger and larger, right? So it's not, you understand what I'm saying. If you look at one neighbor, of course, it's very small, but there are so many of them, right? So that's it.
Okay, sir.
Yeah. I mean, it's the usual thing about funny limits. That's it. So, yeah. This is a peculiar limit. Yeah. So, but in this limit, mean field theory is exact. Any other questions? Any other questions from anyone? Okay. Okay, if there are no other questions, then let me go on. Yeah. So now, let me go on and introduce something else to you, which is the following. So you remember, in fact, I think there was some discussion also when we were discussing mean field. In mean field, we just said that I replace this kind of a quantity by this, right? There was no spatial information here. No spatial information. Okay, and of course, we neglected terms like this, right? These were the two things that we did in mean field theory, right? Okay, so now you see, remember when I showed you those Monte Carlo snapshots as well, right? Of course, if you look at any snapshot of a reasonably big system, then what you see is there are these patches or domains of different sizes, right? And of course, the structures become more and more complex as you approach the critical point, right? So this is a very drastic simplification that you just say that the mean field M is constant throughout space. This is a very drastic approximation. Okay, we'll actually like to go beyond this approximation. Okay, we'll actually like to go beyond this approximation. So now, to go beyond this approximation is possible using again some physically reasonable. What should I say? Physically reasonable conditions. Okay, so let me discuss that. So yeah. So then we'll actually discuss what is known as Landau-Ginzburg free energy. Okay, and again this concept would become very important in your what should I say? In your subsequent treatments, both in field theory and in advanced statistical mechanics and condensed matter. Right. So what is the idea here? So let me explain the idea. And then we'll do some calculations. And we'll also, one of the important things that we'll also derive is the Ginzburg criterion, which actually would tell us why the strange statement occurs. Remember, I made a strange statement that if d is greater than 4 or equal to 4, then the mean field theory exponents are exact. Okay. So even though the partition function is not the mean field theory, right? Because the partition function goes to the mean field theory only when this is true. Okay, right. Okay. So now let us think about the Landau free energy, Landau-Ginzburg free energy. So what is this strange object? Ginzburg. Okay, so what is this strange object? So now this strange object has this property that this M, I don't want it to be a constant in space. In fact, I want to give it a spatial variation. Okay. But there's another thing. The other thing is, you remember, suppose I'm looking at the Ising model and things like that. You remember that apart from the magnetic term, which was like this, all the other terms were like this in the free energy expression that we derived, right? Even powers of M. Why? Because only this term breaks my Z2 symmetry in the problem, and no other term breaks the Z2 symmetry in the problem. So actually that is going to play a crucial role. So basically, you can think of the Landau-Ginzburg free energy simply as a generalization of the mean field theory free energy that we have derived earlier, but with the extra added ingredient that this thing is varying in space. Okay. And then I'll write a free energy expression like this. So because this thing is varying in space, this thing is like this, right? So this x, you can put a vector sign here if you wish, right? Okay, now comes this new term. See, this generalization is very easy. All I'm saying is I just look at my earlier free energy and I just make this m as a function of x. Okay? Right? So there's some spatial variation. But now I write another term. This is like a new term, which I just put by hand. It's a phenomenological term. Okay? So what does this term try to do? And this kappa is positive. Can someone tell me what this term is trying to do? This is, of course, just a gradient of m. Okay?
Sir, I guess it tells that M is analytic near means its neighbors. I'm not able to see.
No, so if kappa is greater than 0, what is this term trying to do? Is it trying to keep the gradient of m as small as possible or as large as possible? No, I mean, I hope the question is clear. Kappa is positive. So this term, is it trying to make the gradient of m as small as possible or as large as possible? What is it trying to do? Sorry, can someone say anything? I'm not asking a very hard question, so I mean, this is a very simple question. Do you guys know what are gradients? Can you please tell me if you know what are gradients? Sorry, can someone please tell me something? Please don't type on the chat box as I've requested you many times. Please just say it. Do you guys know what are gradients?
Yes, sir.
Okay, now comes the second part. This is kappa. Okay, and this kappa is greater than 0. I'm just asking, do you think this kind of a term would lead to a small gradient of m or a large gradient of m? Suppose you just have a theory like this. Forget about all these other terms. Suppose you just have a theory like this. So this is your free energy. What would this theory do?
So large gradient.
Why?
I mean, if I multiply root kappa with grad m,
What is root kappa?
I mean, I can write kappa as root kappa into root kappa, and then I can multiply 1 root kappa with grad m. So if kappa is big, then root kappa into grad m will actually amplify the value of.
Well, I didn't understand the logic. Okay. Anyway, I didn't understand the logic, but okay. Okay, you guys know that the free energy needs to be minimized, right? You know that, right?
Yes, sir.
Now I'm telling you that kappa is a positive number. So what do you want to do on the right hand side? I mean, it's clear
Make
as
it
daylight.
small.
Yeah, so that's it. I mean, you need this guy to be tending to 0, right? That's it. So what this new term is doing is, suppose this guy is not your microscopic state in your Landau theory, in your Ginzburg-Landau theory, but rather maybe you have some state with some fluctuations, like this, maybe, right? Something like this, right? Then this guy is penalizing those fluctuations, right? And the cost of penalization depends on this kappa. This is a phenomenological number. It depends on this kappa. Okay. And this kappa is often also called the rigidity. Why is it called the rigidity? That's obvious, because if this kappa is very large, then of course to deviate from a constant profile of the order parameter m is very hard, right? Because you pay a huge free energy cost. But if this kappa is very small, then of course you allow more fluctuations. Okay, so that's the role of this term. This term is basically penalizing the spatial fluctuations in the order parameter field. Okay, and if the value of kappa is large, then the penalty in the free energy is more. If the value of kappa is small, then the penalty in the free energy is less. Okay, so that's point number 1. Point number 2 is, now this m becomes a m of x. Now it's no longer a number, it's a function. But all of you in your mechanics and all have studied these kinds of things, right? So the right hand side, you feed in a function, and on the left hand side, you get a single number out of it, right? So I'm sure you have done all these kinds of things in mechanics earlier, right? So I hope so, right? So is this familiar with to you, right?
It's a functional.
Yeah, it's a functional. That's correct.
Right.
Yes. So this is familiar to you, right?
Yes, sir.
So basically, in the Landau-Ginzburg theory, what happens is the order parameter, instead of being a number, becomes a function itself. Okay? Becomes a function itself. And all the terms are still dictated by symmetry. So all I'm doing is I'm just generalizing these m naught squares and all that you saw earlier to mx square, mx to the power 4 and so on, right? And I'm introducing this new term here. This new term is simply there because I want to put a free energy penalty, and this makes perfect physical sense. I want to put a free energy penalty to spatial variations of the mean field, right? That field itself. Okay, right. So yeah. Okay, and this is a purely phenomenological theory. This is a purely phenomenological theory. Okay, so many a times you can derive this kappa, A, B, and C, all these things from either experiments or some other calculation, right? But I don't need to know them very carefully. It's almost like saying that you do some Navier-Stokes analysis of your fluid mechanics equations, right? So in your Navier-Stokes analysis, there are many parameters, right? For example, the Reynolds number, the viscosity, and things like that, right? Normally, you derive those numbers using some experiments or some other complicated calculations, right? But they're phenomenological numbers, right? Once you just put in those numbers, you can make lots of predictions using them, right? Especially when you can say what happens when viscosity is high versus low, right? What happens when some other term is high versus low. Similarly, here you can play the same game. You can say what happens when this A is large or small and things like that. So by the way, if you remember, if you recall, in your mean field theory, this A had the crucial property that it was changing sign at the critical point. It was some function like this, some linear function like this. So even here, A would have properties like that. The only thing that changes is now this is a function and now there is this new term. And you should interpret it as a phenomenological theory. Okay, you should interpret it as a phenomenological theory. So is this point clear? I'm of course going to elaborate on it. But is it clear to you that why I'm calling this a phenomenological theory and why I'm introducing a spatial variation in the order parameter field? Because in any realistic situation, as you saw even from those Monte Carlo data, if you look at the snapshot of the spin configuration, right? So after all, this is what we had defined. If you look at the snapshot, then basically there are all kinds of structures at all length scales, right? So if I do this, then I throw out all those structures immediately from my theory, but that's a very drastic approximation. So I want to improve upon that approximation. Okay, that's the rough idea of the Landau-Ginzburg free energy. But again, this is a phenomenological free energy. It's motivated by rules like symmetries and symmetries of the order parameter and things like that. Okay. So please ask questions if something is unclear. I'll of course elaborate on this, but yeah. Any questions at this point? Okay, so if there are no questions at this point, let me try to tell you how to make sense of this mean field theory, even though almost never would you actually do this calculation in the rest of your life. But this is just to sort of set the picture. Okay, so how do you get this Landau-Ginzburg free energy? So one way of thinking about it is the following. So this is one way of thinking about it. Suppose I ask you, how do you calculate the entire partition function from this Landau-Ginzburg free energy? So of course the partition function can be written like this. Let me put A as the real free energy, right? The actual free energy. So the partition function can always be expressed like this. So basically, in terms of the Landau free energy, so again, you're doing some kind of a functional integral here. It looks like this. Okay, in terms of the Landau free energy, it looks like this. So you will understand these things better when you do renormalization group. But let me still tell you the bare bones of what is the meaning of this free energy. Okay. Right. So, but as I said, you would almost never do this actual calculation in any interacting model. But let me just try to say, just let's think of the Ising model. So the Ising model, the microscopic configuration is maybe there's a microstate which is like this, right? In a huge system. Something like this, in some gigantic system. Okay. Now, many of you may have heard the statement that the Ising model is described by a FIFO theory. Essentially, it's basically this theory. Essentially, it's basically this theory where you ignore these terms. And let's say you put the magnetic field equal to 0. Okay. This theory is called the FIFO theory, where M is just replaced by some other notation phi. That's it. So it's a very well-known theory in condensed matter as well as in field theory. Okay. So in the Ising model, the microscopic variables are plus minus 1. But in this FIFO theory, the variables are real valued. Okay. So has anybody heard of this statement? Just to know for my own sake. I mean, of course, I don't expect you to fully understand this, but has anybody heard this statement?
Sir, 5-4 theory is a self-interacting theory, right?
Self-interacting theory. It's
No.
an interacting theory. I don't know what is the meaning of self-interaction, but it's an interacting theory.
Sir, I guess in
Sorry,
sir,
one by one. So yeah, Raj, is that okay? It's an interacting theory. Yes.
Means I wanted to say that if we write the functional form of the phi,
Yes.
then
Functional form of phi.
that means above in the where you have written the functional.
Yeah. Mm-hmm. Here.
Yeah. So there the 5-4 term acts as a source to itself in terms of that.
Source to itself.
If we write the equations of motion.
Okay, maybe it does act as a source to itself. I don't know the language, but okay, it's an interacting theory. It's not a free theory. Okay, so I'm not familiar with this language, source to itself, but okay. Yeah, maybe you're saying the correct thing. Okay, so yeah. Okay, but it's an interacting theory. I mean, it's not a free theory. Any theory which is more than quadratic, right, is not a free theory. Right, that's it. So, yeah. Okay. Okay, so, but I think Akshay, you were saying something.
So I guess this is used in superconductors, no?
Superconductors. No, this is not used in superconductors because in superconductors, the symmetry of the order parameter is something different. So this is not the correct theory for superconductors. So, yeah. Okay. This phi, remember here is a scalar variable. In a superconductor, there's a more complicated theory. It's actually much more complicated because there's also a gauge field involved there. But of course, I won't go into that now. Yeah, it's more complicated. Okay. Anyway, but maybe some of you have already heard this name 5-4 theory. Okay, yeah. Okay, so what is the meaning of this thing? See, the microscopic variables in the Ising model are plus minus 1. But I'm already telling you that this phi or this m, because I'm using these two notations interchangeably, it's a real valued quantity. So what am I even doing? So here, there is an implicit notion. Of coarse graining. So let me try to explain that to you. So what is this implicit notion? So in any such theory, there are two length scales in the problem. One is, of course, the microscopic lattice length scale, A. Let me just denote it by A. So this is the microscopic unit or the lattice unit of the theory. And the other length scale is your correlation length, xi. Right? And of course, if you remember, when we were talking of continuous phase transitions, we said that near the phase transition, the correlation length diverges. This number diverges. This dimensionless number, this becomes much, much greater than that. Right? Okay? We said that. Right? This was one of the properties of continuous phase transitions. So now, we'll do some coarse graining on some length scale L. Okay? Where L would satisfy this property. So this L is much, much larger than the lattice unit of your theory, but it's reasonably small compared to the correlation length. See, why do I want it to be reasonably small compared to the correlation length? Because if this length scale L is very large compared to the correlation length, then basically you lose the sense of the interactions in the theory. Why is that? Because you coarse grain so much, you see 2 points which are separated beyond their correlation length, they are essentially uncorrelated. So if you keep on coarse graining a theory, so this coarse graining is something like a renormalization group. If you keep on coarse graining a theory so much so that this L becomes much, much greater than xi, you actually lose a sense of a lot of important physics in the theory. So you don't want to coarse grain so much. So what do I mean by coarse graining? So you just divide your theory into sort of boxes like this, if you wish. So I'm being schematic. right? You divide your microstate into sort of boxes. Each box has a length L. Like that, right? Okay, so yeah, sorry, was there any? Yeah, okay, so this thing. So now, hi guys, can you hear me again?
Yes,
Hello?
sir.
Okay, yeah, sorry, I had lost my connection. Sorry guys, can you hear me again? Sorry.
Yes, sir. Now we
Yes,
can.
Maybe I'll switch over to my mobile internet because, yeah. By the time I'm doing these complicated things, if you have any questions, just ask me. Sorry. Done. Okay. Yeah. Okay. Yeah. So I think we are back again. Yeah. So now, as I said, when I'm doing this, because of this condition, there are lots of spins here. Now, what do I mean by coarse graining? Now it's simple. I just say the following. So let me just imagine that this is 2-dimension. You can generalize it to any dimension. Just for the simplicity of drawing pictures, it's easy to get do 2 dimensions. So there are sort of L to the D spins here. I just take all the spins here from 1 to sort of L to the D in this box, let's say, and I sum them and I average them out, right? So let's say there are L to the D spins here. I sum all these spins and I average them out, right? So that's why I'm normalizing by L to the D, right? Therefore, this variable is now a real valued variable. It's not an integer anymore, right? And then I replace all these spins here by the single number, m of maybe this I call x1, right? Then similarly, all these guys I replace by that corresponding thing, m of x2, here m of x3, right? So, and so on. So m of x4. So basically, by this coarse graining, I have replaced a microstate by some field, m of x, by some field, m of x. But now, please see the important thing. Now, this is where it becomes more interesting. You see, m. So let me just look here. Let me just look here. So given any value of m here for this box, so given a certain value of mx1 for this box, there are of course more than one microstates present which are consistent with this particular value. Suppose I give you some other value, there are again several microstates which are consistent with this particular value. Of course, there are certain microstates for which only, of course, there are certain values of m of x for which only one microstate is consistent with that. Let me just give you an example. Sum of m, suppose this guy is equal to plus 1. Then what is the microstate which is consistent with this, given this normalization? Suppose I say m of x1 is equal to 1, right? Given this normalization which I've just explained to you, what is the only microstate which is consistent with this?
all size plus 1.
Correct. But suppose I say m of x1 is equal to 0. then is it clear to you? Then what is the condition? What all microstates are consistent with this coarse-grained field? Then it's not just one microstate. Then what is the condition on the microstates which satisfy this?
Equal number of plus and minus.
Correct. And of course, you know that there are many possibilities, right? Because there is a lot of spins here because of this condition, right? Good. Therefore, given any coarse-grained mx field, there are several microstates which are consistent with that particular m of x, right? With that particular m of x, right? So that means that there's a particular entropy, or this is what? This is the number of states, number of microstates which are consistent with this guy, right? There's this particular sort of number of microstates associated with it. Now you can roughly see what is the Landau free energy. The Landau free energy, which I have denoted by this symbol, is basically the energy, because free energy is E minus Ts, given this microstate, given this coarse-grained field, minus T times Kb log of this guy. This is the Landau free energy. So it's a very interesting object. It's almost like I'm giving you a particular coarse-grained coarse-grained field. Now this coarse-grained field m of x is consistent with many microstates. I just take all those microstates and I construct an appropriate, if you wish, partial free energy from that. Right? And then, of course, if I sum over all possibilities of this m of x, then, of course, I get the total free energy. Because then I sum over all the microstates, right? And that is exactly what I have written here, right? That is why this partition function is equal to this thing when you think in terms of the Landau free energy. So it's like a two-step process. In step one, you're actually coarse-graining the problem. You're not interested in all the microscopic details of what each degree of freedom is doing. You see, that's why I'm saying that there is already some sense of renormalization group entering here. You'll, of course, learn these things in more detail later on. So you're not interested in the nitty-gritty details of what each microscopic spin is doing. Rather, you're observing the system at a certain length scale, small l, and the small l length scale satisfies two conditions. It should be much larger than the microscopic lattice spacing of the system, but it should be reasonably small compared to the correlation length of the system. And of course, I satisfy this because I'm looking near the phase transition, and there, of course, xi is much greater than it. So this is okay. Okay, then I take these boxes, right, and then I can associate m of x to each such box, and x is like the center of each box, if you wish. That's like the spatial coordinate of that box, right? So I just add up all the spins and I divide by the number of spins. So m is like the average value of the spin here, right? And of course, the average value here might be slightly different than the average value here, which might be slightly different than the average value here, and so on, right? That's why you need this gradient term, right? Right? That's why you need this term. Right? And basically, given a coarse-grained m of x, there are several microstates which are consistent with that particular m of x. Okay, and that's basically what the Landau free energy is. It's like the partial free energy. It's like the partial free energy that you would have got if you just looked at those configurations which satisfy this problem. Okay, this is basically how the Landau free energy comes. But as I told you, you would almost never do this exercise microscopically for an interacting theory. But if you want to think about it, if you want a physical picture in your mind, this is how the Landau free energy emerges. Okay. Is there any question on this? Any question on this? Okay, so no questions. Okay, but anyway, I mean, maybe of course it'll become clearer to you later on once you do some calculations with it. Okay? So yeah, so this is the meaning of the Landau free energy. Okay, so yeah, let me just write it again. But as I told you just now, you almost never would do a microscopic calculation to derive it. Okay, so then you can ask me, oh, if I don't do a microscopic calculation to derive it, then how can I actually calculate it? Right? How can I actually calculate it? So the answer is very simple. It's again a phenomenological theory. Okay, and you calculate it exactly like you calculate an ordinary mean field theory. These terms are dictated just by the symmetries of the problem. Okay, and basically these values of A, B, C, and all these numbers, you typically derive from an experiment or some other completely different calculation. That's why I gave you the example of this Navier-Stokes equation. In the Navier-Stokes equation, all the properties of the fluid, they are again emergent properties like this. After all, the fluid is also composed of atoms or molecules, right? But things like viscosity, Reynolds number, density, and so on, they are all emergent properties, right? When once you coarse grain the fluid to certain length scales in which you are interested in, maybe centimeters or meters or whatever, right? Then all that microscopic details of the fluid that you care about are hidden in these phenomenological parameters. So this is exactly the same sense in which you should also think of the Landau-Ginzburg free energy. Okay, it's a phenomenological theory. Okay, of course, if you want to microscopically calculate it, you need to do this. But this is incredibly hard for any microscopic interacting theory. It's incredibly hard. Try to do it for the Ising model. There are some steps you will be able to do, but after a point you will fail. So yeah, okay, so. Okay. But the beautiful thing about the theory is that I still know how the terms would look like. This was the great genius of Landau. Basically, to write down the terms, he said that demand that the terms inside are analytic. Then you just use your usual Taylor series expansion techniques, right, to say that something is more important, less important than something. And then the second theory, second thing that Landau demanded was that then only terms consistent with the symmetry of the order parameter are written down. Okay, so this is basically how you construct this phenomenological theory. Okay, you demand that the terms inside are analytic functions. Okay, that's why you are doing these kinds of expansions, right? That's why, for example, you cannot write a term like this here. Let's say d times mod of x. See, mod of x is also symmetric under x, m going to minus m, but mod of x is not an analytic function. Therefore, you cannot write this term. That's the prescription which Landau gave. Okay, and yeah, and then only terms consistent with the symmetry of the order parameter are written inside. Okay? So. Is that fine? At least how you construct this phenomenological thing. You see, this is just a generalization of what you were doing in mean field theory, right? When we calculated everything. And you remember you got a complicated expression, log of cosh hyperbolic of something. And then you expanded it. And then all you got were even powers, right? And that was related to the fact that there is a symmetry of m to minus m in the theory. So the Landau theory, the Landau-Ginzburg theory generalizes that. It just says that now it's a function, it's not a number, but the function the terms inside the function should be consistent with m of x going to minus m of x, right? That's sort of the symmetry when h is 0. M of x going to minus m of x. That symmetry should be preserved, right? When h is 0. That is the new addition. So this is how you write this phenomenological Landau theory. Okay. Of course, this theory is phenomenological. So there is no way I can derive everything for you. Exactly like you cannot derive Navier-Stokes equation from, what should I say, atomic physics or molecular physics. You cannot do that, right? That's too complicated. But it's exactly in the same spirit here. Okay. So, yeah. So maybe it's a good point to pause here because, yeah, there are many sort of new things here. So maybe I'll go on next time. So, yeah. But please, there were some questions. Yeah.
So, what is the length scale we are working with here? Like,
as I said,
what do we observe? Example,
yeah. So suppose you're doing so just give me one moment. Sorry, I'm very sorry. Just give me one moment. There's some. I'll be back. Sorry, in 1 minute.
Okay, sir.
Okay, yeah. So, yeah, let me answer your question. See, suppose you're doing an actual experiment, right? In an actual experiment, let's say again on some system which is described by the Ising model, right? See, whenever you're measuring something, your experiment has a certain, what should I say, spatial resolution. And that spatial resolution is never an atomic length scale, right? You never observe things to that resolution. Exactly like in a fluid. See, in a fluid, you observe the properties of the fluid to maybe some millimeter length scale or maybe some centimeter length scale or something like that. You never observe the actual atoms of the fluid, right? Because you're only interested in the microscopic behavior. So as long as you're just looking for properties, for thermodynamic properties, right, which are not sensitive to the microscopic length scale, but maybe you're looking at for correlation functions which are in which the spatial length scale you're looking at is not A, but small l, right? Something like that. As long as you're looking at quantities like that, it's perfectly okay, right? So basically, any quantity you look at, as long as that quantity does not have too fine a resolution. For example, you're measuring total energy. See, this is the nice thing. If you measure total energy can also be written like this, E1, E2, E3, and so on. Remember, this we discussed in our class. Why? Because then we are only ignoring energies here at the surfaces. But if this patch is reasonably big, then to a very good approximation, total energy is E1 plus E2 plus E3 plus so on, like this, right? So any quantity, any physical quantity which can be represented like this, you can actually do that, right? And actually, this is what you do routinely in experiments, right? Because, yeah. Is that okay? Does that answer your question? Yeah,
yes,
I mean, that's why I'm giving you this fluid example all the time, right? Because that's a very familiar example to you. This is an unfamiliar example. But exactly in a fluid, this is what you are doing when you write Navier-Stokes or whatever, right? This is exactly what you're doing.
So I was wondering, like, if you could give an example of some length scale that we actually work to this on. I mean, is it nanometer, centimeter length scale? What?
No, that depends on your experiment. I mean, right, that depends on your experiment. Any example? Well, I don't know. I mean, suppose you're doing an experiment on a lab.
How small is too small? I mean, what is the length scale here?
How small? I mean, okay. I mean, generally for a magnetic system, this A is of the order of angstroms.
Okay.
You know how much is an angstrom, right?
-10, 10 power -10.
10 power -10 what?
Meters.
Okay, right. So now if you're observing your system, right, at let's say a micrometer length scale or a millimeter length scale, then you understand what I'm saying, right?
Yes, sir.
Yeah, that's it. Okay, that's it. Is that okay?
Okay, sir. Thank you.
See, because never in a magnetic system do you measure any correlation length to angstrom level. This never happens. Okay. Because you're looking at some macroscopic property, let's say the total susceptibility or the total heat capacity and things like that. So you never look at the system to that resolution. Okay. So, yeah. Actually, what I'm trying to say is even if you did, it doesn't matter. It'll be just that you have too much information. See, okay, this is an important point. I mean, okay, again, suppose you look at this fluid example that I talked about. Of course, if you know the velocities and positions of each atom, of course, you can take that information and do some complicated thing and tell me what is the macro motion of the fluid. You agree with me, right? Because given the microstructure, you can tell me the macrostructure. The other way around is not possible. Given the macrostructure, you cannot tell me the microstructure. Why? Because you see, as I said, given a field m of x, there are many microstates which are consistent with that. You see what I'm saying? Is that clear to you? You see what I'm trying to tell you, right? Yes, see, you should not have the impression that if I have all the details and I'm doing a superb experiment where I have all the resolution, then I cannot do this procedure. Of course, you can still do this procedure. Because from a microstate, you can always go to a sort of a coarse-grained description. The reverse is not true. That is very difficult to do, right? But the point is, because you're interested in macroscopic physics and macroscopic behavior, you don't need to store all that information. Because none of the quantities that you can reliably talk about, right? They don't care about all that information. They only care about the part of that information, right? For example, the density of a fluid. That does not care about all the information that where this atom is, where that atom is and all that, right? It doesn't care about that, right? It only cares about the certain bare minimum information, okay? Right? So, right. Any other question? Any other questions? Okay, so next time we'll see that writing this Landau functional and then doing some calculations using that, we'll actually see two things. First, so this is something which we did not see earlier. First, that the correlation length diverges like this near the critical point. You remember, right? As within mean field theory. So why couldn't we derive this result earlier? Why couldn't we derive this result earlier? There's a very simple reason. We couldn't derive this result earlier. To derive this result, we need to define the correlation function. But earlier, so we needed to look at this kind of an object, right, to derive this result. But earlier, we said that this guy is a constant in space, right? And this m naught. So yeah, so it was very hard for us to get this information out, right? So we'll derive this in the next class, that this is true, okay? So that's one thing. The second thing is that we'll actually motivate this Ginzburg criterion. So what is the Ginzburg criterion? It tells you when is mean field theory good for calculating the critical exponent. So what is the rough logic? So see, in mean field theory, I had ignored the fluctuations, right? That was the approximation in mean field theory. So now I'm including the fluctuations in a certain manner. I'm putting this gradient term. So that's including fluctuations in a certain manner. Now what I'll do is calculate the contributions due to this fluctuation. Okay, I'll calculate the contribution due to these fluctuations. And then what I'll demand is that mean field theory can only be accurate if these fluctuations are themselves small within this framework of Landau-Ginzburg theory. So what I'm demanding is self-consistency of the theory. Okay. What I'll then see is that for D less than 4, this will not be true. So the theory will tell me its own, the theory will itself tell me when it's not valid. The theory will itself tell me when it's losing its consistency. Okay. And whereas for D greater than 4, you will see that miraculously the theory will be self-consistent. And then the answers would make sense. Okay. So we'll see all that in the next 2 lectures. So that's the goal. Okay. And yeah, so the short-term goal is to derive this result for the correlation length. Because earlier we could not even define this in principle because there was no spatial structure in my theory, right? But now I can define this because this m of x is a function of space. So I can define correlation functions like this. I can define them, okay? Okay, so this is what I wanted to tell you today. So if there are any quick questions, you can ask me. Otherwise, we'll meet again on Wednesday. And if you have more questions, then you can always ask me at that time. So, yeah. Okay? Is that fine?
Yes, sir.
Okay, okay. So that